All right, welcome back, focused learners. Let's just jump right in today because we are tackling the absolute bedrock of any credible study. Whether you're scanning a medical journal, checking the latest political poll, or digging into a massive demographic report, there's this one, often invisible decision that dictates whether you can trust a single word of it, and that is sampling. We're going to look at how these decisions can literally make or break research credibility. We'll explore who gets counted, who gets left out, and how researchers mathematically actually prove their findings.
Okay, picture this nightmare scenario. You spend months and literally thousands of dollars collecting data, running these brilliant statistical models, and drafting an incredible report. But then you realize that the people you surveyed don't actually represent the population you're studying. So what happens when your sample systematically excludes the truth? Well, your research basically corrupts the data, and your conclusions become dangerously misleading. Okay, let's dive into this and make sure that never, ever happens to you.
So here is our roadmap for the explainer today. We're going to systematically work our way from the ground up. We'll start with foundations and frames, move into probability methods, then non-probability techniques, determining sample size, weighting and generalizability, and we will wrap it all up with a practical sampling decision framework.
First things first, Section 1, Foundations and Frames. This is the core challenge of inference.
The core challenge of inference really boils down to understanding exactly who you're trying to study versus who you actually have access to. Think about it. Your target population is totally separate from your sampling frame. Your target population might be, say, all primary school teachers in a country. But your sampling frame, that's the actual physical list you draw from, like a government registry. And that gap between the two? That is what we call coverage error. Because if your registry is outdated, it might systematically exclude, let's say, informal sector workers. And that fundamentally biases your estimates right from day one. Your math can be absolutely perfect, but if your frame is flawed, the whole dataset is compromised.
So how do we fix that? Let's get into Section 2, probability sampling methods, and how they evolve in complexity.
Once you have a frame, how do you actually choose the right people from it? Well, the undisputed gold standard here is simple random sampling, or SRS. This is our pure, beautiful mathematical baseline. Every single individual in the frame has a perfectly equal, non-zero chance of being selected, usually by just using a random number generator. It is statistically unbiased, which is great, but here is the massive trade-off. Unless you have an unlimited budget to randomly fly researchers across an entire country to survey scattered individuals, it is an absolute logistical nightmare for large, geographically dispersed populations.
Which brings us to the precision fix, stratified random sampling. Instead of just blindly pulling names out of a giant hat, you first divide your population into homogeneous subgroups. We call these strata, like urban and rural. Then you pull a random sample from within each of those groups. This mathematically guarantees that critical minorities or specific subgroups are properly represented in your final data, without leaving it completely up to chance.
But what if your population is scattered across 50 different districts? You still can't afford to travel to every single one of them. Enter cluster sampling. This is the geographic fix. You divide the population into naturally occurring groups, like schools or entire villages. You randomly select a few of those clusters, and then you just survey everyone inside them. It drastically cuts your field costs. But, and it's a big but, people living in the same village tend to be similar. They share local economies, they share environments. This intra-cluster similarity introduces a design effect, which actually increases your sampling error. So you save money on travel, for sure, but you have to survey more people overall to keep your math sound.
Now, when you're doing massive, national-level studies, like the demographic and health surveys, you need the ultimate scalable design, which is multi-stage sampling. This method basically hierarchically stacks everything we just talked about. So you might randomly select districts, then randomly select villages within those districts, and then randomly select households within those villages. It perfectly balances the massive logistical reality of a nationwide study with the absolute rigor of probability math. And taking a step back, you can really see the entire evolution of complexity we just walked through. Probability methods progressively adapt to reality. We start from the baseline randomness of simple random sampling, we step up to the precision of stratification, we adapt to geographic realities with clustering, and finally scale all the way up to massive multi-stage designs. Every step makes the study more logistically feasible, but, and you really have to remember this, it crucially also adds complexity to how you calculate your variance at the end.
All right, shifting gears a bit. Section 3, non-probability techniques. This is where we find qualitative depth.
So what happens when statistical math just isn't your primary goal? There's this super common misconception that probability sampling is always superior. It's really not. If your goal is statistical inference and massive breadth, then yes, absolutely use probability. But if your goal is analytical generalization, like exploring a really complex context or building a brand new theory from the ground up, then non-probability sampling is completely indispensable. This is where you rely on researcher judgment rather than known selection probabilities.
The absolute backbone of this kind of qualitative inquiry is purposive sampling. This is where researchers completely abandon random chance. Instead, you strategically and intentionally select information-rich cases based on highly specific criteria. So you might look for the most extreme cases, or aim for maximum variation, or you might specifically seek out recognized experts. You aren't trying to mathematically represent a population here, you're trying to build a robust, deep theory.
And then we have snowball, or chain referral sampling. Think about it. How do you survey undocumented migrants or informal workers who aren't on any official government registry? Well, you find one person, you build trust with them, and you ask them to refer someone else in their network. It is a brilliant way to access hidden groups. But you really have to be careful. Because people tend to refer friends who are just like them, this carries a massive risk of homophily bias. Basically, birds of a feather flock together, meaning you might only get one single perspective. To mitigate this, you absolutely must strategically start with multiple, highly diverse initial seeds to spread those referral chains out as much as possible.
Okay, moving on to Section 4, determining sample size. It is time for some myth-busting and talking about saturation.
You have probably heard this specific number thrown around a lot, 384. It gets touted all the time as the universal, magic sample size for quantitative surveys. But I'm here to tell you that is a massive myth. 384 is just a standard formula that assumes maximum variability, a 95% confidence level, and a 5% margin of error. Literally, as soon as you introduce clustering or design effects, or if you just need higher precision, this number completely changes. It is absolutely not a magic one-size-fits-all rule.
And when we switch over to qualitative studies, the concept of sample size is just an entirely different beast. You aren't chasing statistical power at all, you're chasing thematic saturation. Recent reviews actually suggest this generally takes about 5 to 30 participants per homogeneous group. But honestly, the exact number doesn't matter. What matters is iterative sampling. You keep recruiting and you keep analyzing until absolutely no new properties, dimensions, or insights emerge from the conversations. That is when you know you have enough.
Which brings us to Section 5, weighting and generalizability. This is all about correcting the math after the fact.
Because the reality is, once your data is actually collected, the work still isn't done. Ask yourself this: even if you designed a perfect probability study, what happens when selection probabilities end up being unequal in the field? Or what if certain groups, like rural workers, systematically fail to respond to your survey? The crucial point is that suddenly your sample is misaligned with your population. You have to fix it, and you do that through statistical adjustment.
You can kind of think of weighting like a giant balancing scale. Use design weights to correct for the unequal selection that was built into your method. Then you use non-response adjustments to rebalance any groups that didn't participate. And finally, use post-stratification to align your final demographics with known external benchmarks, like a recent national census. This whole process mathematically restores your external validity. It pulls your estimates right back to the truth. Just keep in mind, while weighting is amazing at fixing bias, it does inevitably increase your statistical variance.
Finally, Section 6. Let's pull this all together into the sampling decision framework.
We've covered the heavy theories and the math, so now let's look at a highly practical decision tree. This diagnostic flowchart completely demystifies the whole research design process by framing it as a series of simple if X constraint, then Y method choices. You start by defining your target population precisely. Then you ask, do you have a complete list available? If the answer is no and the population is geographically dispersed, you're immediately looking at multi-stage or cluster sampling. If you do have a list, but specific subgroups are absolutely critical to your research, you instantly route over to stratified random sampling. It really forces you to align your chosen method with the harsh reality of your available data and resources.
Ultimately, the entire explainer boils down to these two core directives. Number 1, match your method to your constraints. Please, don't chase some mathematical ideal if you don't actually have the sampling frame to support it. And number 2, anticipate the design effect. If you decide to use cluster sampling to save money, you just have to know that you're going to need to bump up your overall sample size to compensate for that intra-cluster similarity. And that brings us to the most important takeaway of all. Transparency is credibility. The validity of any statistical generalization rests entirely on methodological transparency. Have you fully documented your frame errors? Have you clearly stated your weighting procedures? I want to leave you with this lingering question to evaluate your own future work. Is your sampling methodology transparent enough to be credible? Because let's face it, a brilliantly analyzed, massively funded study that's built on a hidden, biased sample is basically worthless. Sample smart, document absolutely everything, and research rigorously. Thank you so much for joining me on this explainer, and I will see you next time.